All right, hello everyone again. We already have finished chapter 6, the second law of thermodynamics. This is part 5 and part 6. In these two parts, we are going to go over some sample problems. So before that, let's summarize what we had in the previous parts 1 to 4. So first we talked about a heat engine. For a heat engine, as schematically you see it on this slide. So the heat engine is like a combination of multiple devices such as like a power plant, an internal combustion engine, any other device that receives heat from a high temperature reservoir. It receives QH, generates some work, W net out, and rejects the rest of the energy to the surrounding to a low temperature reservoir. So if we write the energy balance, the first law of thermodynamics for the heat engine, we see that energy coming to the system is QH is equal to energy out, which is W net out plus QL. So W net out plus QL is energy out equal to QH, which is energy in. This is a cycling process. Therefore, delta E or delta U for this process, according to the first law, is equal to 0. And it's like we are considering the concept of a closed system for this heat engine. So there is no mass in, mass out. However, we should know that inside this closed system, we do have multiple devices that operate based on a control volume. So in order to analyze the whole thing, we assume that the whole thing is enclosed in a system. And then in order to analyze each device separately, we assume that each device follows a like control volume or open system concept. And in this particular case, like in the case of a power plant that you see here, the devices work based on a steady flow process. So for the heat engine, the efficiency is W net out, the desired output. What do we expect to get from a heat engine? It's the W net out, which is the work of turbine minus the work of the pump, divided by the total input, the total heat input, which is QH. So it's simplified to eta thermal equal to 1 minus QL over QH. And then we said that for the reversible ideal cycle, which is called Carnot cycle, QL over QH is replaced by TL over TH, where these temperatures are in Kelvin, and the efficiency of the Carnot cycle is obtained from this equation, 1 minus T sub L over T sub H. Similarly, if we reverse the processes, a heat engine will be converted to a refrigerator or a heat pump. So in this case, the idea or the requirement or what is desired is to actually extract some heat, QL, that's the desired output. For this to happen, we need to provide input work to the system, such as the compressor work in the case of a refrigerator, and then this will become possible to transfer the QL to the high temperature environment, which is at a temperature TH. So for this system, the first law mandates that the energy balance, energy in equal to energy out, delta U again is 0. So energy in is QL plus W net in that you see here is equal to energy out, which is QH out, or QH, sorry. So efficiency in this case is defined differently. we cannot define a regular efficiency. Instead, we define coefficient of performance. And for the case of refrigerator, COP is defined as the desired output divided by required input. So for refrigerator, the desired output is QL. And the input is W net in, for instance, the compressor work. So if we go ahead and substitute W net in by QH minus QL in this equation and divide all terms by QL, we end up with this equation where COP refrigerator is 1 over QH over QL minus 1. This is for any refrigerator, actual refrigerator. Now, if we assume that the refrigerator works on a Carnot cycle, all of the processes are reversible, then the efficiency will be, the COP will be simplified or will be converted to this form. We just replace QH over QL by TH over TL. In the case of a heat pump, everything is similar to a refrigerator, except that for a heat pump, the desired output is actually cooling, is actually heating the space. So the desired output is the QH that we provide to the the house interior. So COP is defined differently for a heat pump, QH over W net in, and the rest of the process is similar. So you may ask, what's the use of a heat pump? Why we do not use a resistance heater? If we do use resistant heater, then W net in, the electrical work in a resistant heater, will be directly converted to heat. However, if you use a heat pump, then you will be able to actually boost this amount of work in and extract some additional heat from the cold surrounding and then pump that heat to the interior of the house. So in this case, in the case of a heat pump, QH is actually equal to W net in plus QL. So it is to our benefit to use a heat pump instead of a resistance heater, because in the case of a heat pump, we can actually provide more heat to the house with the same amount of the electricity bill. So now the question is that why some people still use resistance heaters? The reason is that the capital cost of a heat pump is much higher than a resistance heater. So a heat pump is like a long-term solution. A resistance heater is a short-term, low initial cost solution. And by the way, heat pumps do not work at very cold winters. So if the outside temperature TL is very low, then a heat pump does not, then the COP of the heat pump will not be high enough. So in very low, in cold, climate, the heat pump is not a good solution. Okay, so now with this, let's go look at two problems in this part and then two more problems in the next part. So this is problem 628 of the book. We do consider a coal burning steam power plant. So it's a heat engine. Produces a net power of 300 megawatts with an overall thermal efficiency of 32%. Okay. So we do have the W net out and we do have the efficiency. The actual gravimetric air fuel ratio, the mass of air over mass of fuel in the furnace, furnace of the boiler is calculated to be 12 kilogram of air per 1 kilogram of fuel. The heating value of the coal is 28,000 joules per kilogram. It doesn't mention low heating value or high heating value, it just mentions the general heating value. So with this given information, determine the amount of coal consumed during a 24-hour period and the rate of air flowing through the furnace. So I suggest that you pause the video at this time and read the question one more time so that you understand the question very well before moving to seeing the solution. Okay, so as we said, this is a non-ideal heat engine. It says it's a power plant, but power plant is a kind of heat engine because it receives heat, generates work. So all equations that we have shown and derived for a heat engine is applicable to a power plant. So we assume that the power plant operates in a steady flow process. So it's steadily. Kinetic and potential energies are assumed zero because there was no information about kinetic and potential energy, and usually they are negligible. And the heating value of the fuel is given. All right, so the efficiency of the power plant is given, and also the net work out is given. So we can go ahead and use the definition of efficiency and find efficiency is W net out divided by Q in. So therefore we can write it in this form as well. Everything is the system, sorry, this heat engine works on a steady flow process, so we can use the same equation in the rate form. So Q dot in is equal to W dot net out divided by the efficiency. So we do have the net output. This is the power given to the generator of the power plant divided by the efficiency. So we find Q dot in. This is in fact Q dot H of the heat engine. So we are going to calculate these values over 24-hour time period. Therefore, we go ahead and multiply Q dot in by delta T, the number of seconds available in 24 hours. So we multiply the power Q dot in by 24 by 3,600 seconds. So this will give us the total amount of energy provided by coal burning over 24 hours. 8.1 times 10 to the 7 megajoules. So the question asks us to find the amount of coal per 24 hours. So we do have Q in, we just calculated. If we divide it by the heating value of the coal, so heating value is how much heat the coal can provide per kilogram of the coal. Then we find the amount of the coal, 2.893 times 10 to the 6 kilogram for a 300 megawatt coal power plant. So this is a lot of coal, and it obviously it does have a huge carbon footprint. So if we want to find the mass flow rate of the coal, we divide it by delta T, which is 24 hours, and we need to convert it to seconds. So mass of the coal divided by 24 hours and then multiply by 3,600 seconds. This will give us the coal mass flow rate in kilogram per second. The problem also asks us to calculate the air flow rate. So in order to find the air flow rate, we note that in the problem, the air-fuel mass ratio is given, which is 12. So the ratio of air to fuel is 12. So if we multiply the coal mass flow rate by 12, then we can find the air mass flow rate as given here. So this is a kind of like moderate problem that you may expect from this chapter. So straightforward. If you notice, we didn't use the Carnot cycle. So this power plant is an actual power plant, and we didn't have to use, I mean, because the problem didn't say that it's ideal, so we didn't use the formulas for the Carnot cycle. So it's not the case here to use the Carnot cycle. Okay, so let's do another problem. In this one, this is 654 of the book. Refrigerant 134A enters the condenser of a residential heat pump at 800 kilopascal and 35 degrees C. So it enters the condenser. So here we are talking about this point. That's the exit of the compressor and entrance of the condenser. So here there is another chance to review the components of a refrigerator, which are the same as the components of a heat pump. So if a refrigerator has a compressor, it compresses the gas, its pressure increases, temperature also increases, then it enters a condenser in order to give away heat to the surrounding Q.H. At the exit of the condenser, in this particular problem, the pressure is still the same. We assume that pressure drop is negligible. But what happens is that in the condenser, a phase change process occurs. So at the exit in this particular problem, X is equal to 0. So it means that the refrigerant will be saturated liquid at this given pressure. Then the saturated liquid enters an expansion valve, or like a coil of capillary tubes, and the idea is to reduce the pressure, to break down the pressure. So while it still remains liquid, so as it passes through the expansion valve, the pressure drops at the exit of the expansion valve, but it's still liquid. It's still saturated liquid or very close to being saturated liquid. And it's now ready to go to the evaporator and absorb heat from the low temperature reservoir or evaporator. So it undergoes another phase change process. It absorbs a lot of heat. As a result, it can keep the refrigerated area cool. And at the exit of the evaporator, it is usually in the gaseous form, like saturated refrigerant. So, and then it enters the compressor. It is compressed. Its pressure increases to a higher level. So now it's ready to undergo another phase change process, but at a higher temperature. At this time, 35 degrees C, it's like almost ambient temperature, much higher than the temperature of the evaporator. Okay, so this was a good review of a refrigerator and also heat pump. So now gets back to the problem. So the mass flow rate is given, and the pressure at the exit of the condenser is given. So if the compressor consumes 1.2 kilowatts of power, so we do have W dot in. Determine the COP of the heat pump and the rate of the absorption from the outside air. So first of all, we are using it as a heat pump. So it means that the desired output here is Q dot H, as COP of a heat pump has to be used. So the purpose of using this equipment is actually to provide this Q dot H to, to the, for instance, to a heated area. So even though we are using refrigerant, but actually the cycle is a heat pump. So this, in other words, the cycle for a heat pump and a refrigerator is the same. The purpose is different. So if you just, depending on whether you want to cool the area here, so if you want to cool this area, then this is a refrigerator. If you want to heat the area here, then the device is called a heat pump. So this is like you can actually switch. In some areas, the same device is used, and in the winter, the condenser part of it is used as the desired output, and then in the winter, the condenser part is used as the desired output, and in the summer, the evaporator part of it is used. Now you may say, how to do that? Do we need to turn the entire, device in the winter and summer? Well, you could do that, but usually what happens is that the device does have a switch, like a valve, a kind of valve that can switch the direction of the refrigerant in the cycle. So condenser and evaporator remain the same, but since the direction of the refrigerant changes, the function of the condenser and evaporator switches in the winter and in the summer. So physically, we don't have to turn this device, it remains the same, but by changing the direction of the flow, basically the functionality of the condenser and evaporator switches in as we turn on or off the valve. Okay, so now let's do this problem. So we do have the refrigerant entering the condenser at given conditions and leaving the condenser at given conditions. It's so the flow of the refrigerant is known. We want to find the COP. The power of the compressor is also known. We also need to find the rate of heat absorption from the outside air. So you can go ahead and pause the video now, read the question again, and then go back and see the solution. All right. So we said that we do know the condition at the condenser inlet and condenser outlet. So this will help us to find QH or Q dot H. The assumption here is that all of these components work on a steady flow process, and also the kinetic energy and potential energies are zero. So we do need to use tables. The tables are given in the following slides, but I cannot switch back and forth between the slides, so later we will see the tables. So P1, T1 is given. We do need to use the saturated, we do need to use the refrigerant table for the superheated gas. So this is here, the gas is superheated at the exit of the compressor or inlet to the condenser. So with given pressure and temperature, we can go ahead and read H, the enthalpy of the refrigerant, H1. So this is 0.1. And then at the exit, the problem asserts that X2, the quality is 0, so it's saturated liquid, and the pressure is still 800 kilopascal. So we do need to use the saturated table for refrigerant, tabulated based on pressure. So the saturated table for refrigerant, the pressure table. So then we can go ahead and read H2 from the table, and H2 is equal to HF at 800 kilopascals. So we do have the tables in the following slides. Okay, so what is the use of finding enthalpy at point 1 and point 2? And point 2 is just right at the exit of the condenser. So if now we write the first law of thermodynamics for the condenser, this is a steady flow device, open system or control volume. So the energy in, the rate of change of energy in is equal to the rate of change of energy out. So energy in is m dot h1, energy out is m dot h2 and q dot h. So this q dot h, if I put a dot on top of it, so as a result, q dot h, energy out per unit time, is equal to m dot h1 minus h2. And we already found h1 and h2, so we can go ahead and find q dot h. So that's the amount of the heat given away by the condenser and provided to the heated area. So one part of the question asks to find COP. So COP for a heat pump is Q dot H divided by W dot in. So we just found Q dot H, and W dot in is the compressor work. So the COP of heat pump is 2.64. Another part of the problem, it asks us to find the rate of heat absorbed from the outside air. The rate of heat, so that would be Q dot L. And in order to find Q dot L, we can write the energy balance for the entire system. So for the entire heat pump, so energy in, which is Q dot L plus W dot in, is equal to energy dot out, which is Q dot H. So Q dot L is equal to Q dot H minus W dot, which is now found. So two other things that I'd like to talk about is how to find H1 from the superheated table and how to find H2 from the saturated table. So this is for finding H1 at the beginning of the condenser or exit of the compressor. So you go to this superheated table for refrigerant 134A and look at the pressure 800 kilopascal. This is the pressure segment, and the temperature, the desired temperature is 35 degrees C. So in the table, you do have the properties for saturated temperature, which is 31.3, and then the next available data point is 40 degrees C. So, but we do need this property H1 for 35 degrees C. Therefore, we would need to interpolate between the saturated temperature 31.3 and 40. So therefore, we go ahead and do linear interpolation. At temperature 31.31 degrees C, H is 267, given here. At 40 degrees C, H is 276, which is given here. Then we just simply go ahead and interpolate in order to find H at temperature of 35 degrees C, which is in between. So just follow the linear interpolation that we talked about in the previous lectures from chapter 3, 4, 5, and so on. So with this, we can find H1 by interpolation 271.22. And the last thing that I'd like to talk about is how to find the enthalpy at the exit of the compressor, at the exit of the condenser. At the exit of the condenser, the pressure was given 800 kilopascals and quality was given as 0. So it means that we are looking at a saturated liquid condition. So if we now go to the saturated refrigerant pressure table and look at the pressure of 800 kilopascals, then H2 would be equal to HF. Because quality is 0, enthalpy would be simply equal to HF. So this 95.47 is H2, which was used in the calculations in the previous slides. So this brings us to the end of this part 5 of chapter 6. We do have another last part, part 6, which is going to be a shorter part. We will go over 2 more problems, which will conclude this chapter. Thank you for your attention.